I'm going to discuss a different way of getting to Poynting's theorem. And we're going to start by looking at the Ampere-Maxwell equation in the form curl of H minus dd by dt is equal to J. That's simply the standard form, but I've moved the fields to the left and the sources to the right. And we're going to start from Faraday's law. Curl of E plus dB by dt is equal to 0. Excuse me. So let's just realise, or start by thinking that we note, if you prefer, that E dot J has the dimensions of a power per unit volume. And if we're interested in thinking about how energy flows, then E dot J is going to be a useful thing to think about. Now, how would we get to E dot J from those equations? Well, if we take the first equation and dot it with E, we find E dotted with the curl of H minus E dotted with dd by dt is equal to E dot J. I'm going to label that equation 1. Now, if we want to get a similar equation from Faraday's law, to get the units of power per unit volume, we have to dot that with H. You can see that just by comparing the two. So if we do that, then we get H dotted with the curl of E plus H dotted with dB by dt is equal to 0. And I'm going to call that equation 2. Now, if we take the difference between these two, so if we take 2 minus 1, then we get the following. We get H dotted with the curl of E minus E dotted with the curl of H plus H dotted with dB by dt plus E dotted with dd by dt is equal to minus E dot J. There is a standard theorem of differential calculus and the vector differential calculus that says that these two terms, those first two terms there, H dot curl E minus E dot curl H, is equivalent to the divergence of E crossed with H. And so we can substitute that, at which point we find the following. Let me just get rid of that. The divergence of E cross H plus H dot dB by dt plus E dot dd by dt is equal to minus E dot J. And I've shown in the other video on Poynting's theorem that you can write these two terms as being equivalent to d by dt of a half H dot B plus a half D dot E. And it's fairly easy to do for a linear homogeneous isotropic material. And so we finally end up with the following. We have that the divergence of E cross H plus d by dt of U, that's the energy density, and remember that this term in the brackets here, a half H dot B plus a half D dot E is the energy density, is equal to minus E dot J. So this so far has simply been a manipulation of two of Maxwell's equations. We're now going to integrate over the volume containing the fields. So we get the volume integral of the divergence, and that should be setting off alarm bells, of E crossed with H dV plus the time derivative of the volume integral of the energy density is equal to minus the volume integral of E dot J dV. And of course we're going to apply the divergence theorem to that first term on the left-hand side, and we're going to say that the closed surface integral of E cross H dot ds plus d by dt of the volume integral of the energy density is equal to minus the volume integral of E dot j dV. The quantity, as I said in the other video, E cross H is often referred to as Poynting's vector. N is equal to E cross H. We define the closed surface integral. That's a closed surface integral of N dot ds as the outward flux of energy through the surface. And it's that identification that leads us to also suggest that Poynting's vector can be identified with the flow of energy per unit area, though that is actually only a tentative identification. And so what we're seeing here is that the three terms in the equation, the first term gives us the outward flow of energy through the surface, the second term gives us the time derivative of the stored energy, and those two between them must be equal to the minus, must be equal to the work done by the fields. So if the fields are doing work, then you should be increasing the energy and energy should be flowing in. If the fields are doing the opposite of work, no, sorry, not doing the opposite of work. If the work done is negative, then we are storing energy and we are bringing energy out of the field. Sorry, that got a little bit confused. Look at the meanings of the individual terms. So the first term is the outward flux of energy. The second term is the change with time of the energy stored. So if that's positive, more energy is being stored. And on the right-hand side, we have minus the power, i.e. the rate at which work is being done. And if we are doing work with the fields, then we would expect the energy stored in the fields to decrease, which is why there's a minus sign between those two terms. If energy is flowing out of the volume where the fields are, again, that indicates that we are getting work out rather than putting work in. That's a better way to phrase it. So if the fields are doing work on a volume, then the energy will be flowing into that volume. We'll be storing more energy in that volume, and therefore all of those signs make sense.